Hello children, how are you all? Hope you all are fine and doing well. Dear children, in this session we are going to discuss all about simple pendulum. So under this simple pendulum concept, first we will be learning what is a simple pendulum, the terms related to the simple pendulum. Then we will discuss how to calculate time period of a given simple pendulum and on which factors does a time period depends, and on which factor it does not depend also we will discuss, and finally how can we calculate the acceleration due to gravity at a given place by using the simple pendulum. Just here, look at here, this is the arrangement setup of actually simple pendulum. Here you can see that here is a rigid support, here is a string, and this is a heavy point mass. Then how to define actually simple pendulum? What is simple pendulum? Dear children, a heavy point mass is suspended from this rigid support by means of a string is called simple pendulum. I repeat once, heavy point mass is suspended from rigid support by means of a string is called actually simple pendulum. The first thing is that, dear children, heavy point mass is not actually existing. It do not exist actually, means heavy like a point mass, it's not possible. It's like ideal case only it is. So heavy point mass is the ideal case. And it is that it is suspended by means of string. But what type of string we should take here? So dear children, so before going to consider string, so it should have actually these properties here. So the string whatever we are considering should be inelastic. So as it is inelastic, dear children, you know what happens during its oscillations, the length of the simple pendulum remains constant. If it is not inelastic, what happens during the oscillations, the length may change. As length changes, obviously time period changes actually. So it should not, there shouldn't be any change in the length of the simple pendulum. So it is possible only when we take inelastic string. And the first one. Second, it should be massless actually. Children, actually massless is not, it's not at all possible here. Do you think that a string can exist without mass? It is not that. So massless means what here? It is like a, a lightweight, means the total weight of the simple pendulum only due to this heavy point mass only, means when compared with the mass of this bob of the pendulum, the mass of the string is negligible. So we have to understand in that way. So it does not mean that mass means a zero mass. No, it's not that. When compared with this bob of the pendulum, the mass is negligible. And third one is torsionless. Torsionless means what, children? For example, if there is some torsion, then what happens, that will be like, rotating like this. It will be rotating. So it shouldn't be actually. So if thread with a torsion, it will rotate. It will rotate. So torsionless means what, children? It won't rotate like this actually. So these three should be like, properties of the string which we are going to consider. So whatever the string which we are considering, children, it should be inelastic, massless and torsionless. Now we will see some terms related to the simple pendulum. First, we will discuss what actually oscillation. Children, it is important, very, very important. So understanding what actually oscillation. When you can say that a simple pendulum has completed one oscillation. Children, here OA is a mean position. When this simple pendulum is taken to the point B, like I said, either you can take a left side or a right side. When it is left, what will happen? It will be in motion. Of course, such type of motion we can call the oscillatory motion here. Now for suppose, dear children, it is at a point B. Children, here point B and C are called extreme ends, extreme points, whereas OA is called actually mean position. Now, if this simple pendulum is taken at a point B and it is left, so it is doing oscillations. Now, let us try to understand. Initially, it is at a point B, let us think. So, it is at a point B, for example, it is at a point B. So, when it is left from here, then what will happen? It will go to the point C via point A. So, it will go to the point C. Again what happens? It comes back due to the gravitational pull. Again it comes back to the point B only. But don't forget that it is going B to C via point A, again C to B via point A only. So then we can say that it has done one oscillation. Means it is two motion and it is a fro motion. So here one complete to and fro motion of the bob of a simple pendulum is called one oscillation. Children, repeat, what is oscillation? One complete to and fro motion of that bob of a simple pendulum is called actually one oscillation. But children, don't you think that from point B to go to point C, again to come back point B, that is to complete one oscillation, it takes some time, right? So that only we can call it as a time period. So children, next word which is very important, that is a time period. What is time period? The time taken to complete one oscillation will represent with a capital T. So children, so from point B, it will go to point C, again comes back to point B. Then we can say it has done one oscillation. So to complete one oscillation, so the time taken by the bob of a simple pendulum to complete one oscillation is called time period. That is fine. But dear children, here we get one doubt actually. So to make it an oscillation, we have to take this bob of the pendulum aside, right? But to what distance we have to take from its mean position? Here, here, here. It is not that. You make it one doubt. Sir, this bob is there. I will hold and I will take till here. I will leave it. What happens? Of course, it may do oscillation, but not in a proper way. What happens? For example, here, let me try to take something like this. Let me tie up this, what we can say. Yeah, here is thread is available. And let me take this ink bottle. Fine. Children, look at here. For example, let us take, just think that it is a bob of the pendulum. It is a string. It is a string. So, I told you that when it is taken aside, so it is left. So, what is happening? Look at here. From here, it will go to here, again come back. Then we can say that it has one oscillation. To go to here and to come back here, it takes some time. That time taken only we can call it as a time period. But the important thing is that here, for example, if it is taken like this, okay, it will do some oscillations, no problem. But if I take till here, what happened? Children, it is like, it is like a oscillating, at the same time it is jumping like this. It is like a jumping like this. Means here it won't do the proper oscillations. But here, what is the condition for that actually? Till what extent actually we can take aside? Children, such a way that this angle should not exceed 5 degrees. Children, this angle from this mean position should not exceed 5 degrees. And moreover, dear children, here from this mean position to this maximum from this point, from mean position to the extreme position, either left side or right side, we can call it as a amplitude. Children, this we can call it as a amplitude. So next term, what we have to learn? So it is a amplitude. It's very much important here. Amplitude. Children, what is amplitude? The maximum displacement of the bob from here to here. We are taking the extreme position, right? So from here to here, this maximum displacement of the bob from its mean position is called amplitude. So we have to take the bob aside, either left side or right side, such a way that this angle should not exceed 5 degrees. Children, once again let us recall what is amplitude. The maximum displacement of the bob of the pendulum from its mean position is called amplitude. Fine. But dear children, here one important thing is that, okay, it is pulled aside, either left side or right side, and it is doing oscillations. That's fine. But can we count the number of oscillations done in 1 second? Of course we can. Of course it depends on its length. It may do 1 oscillation, it may do 2 oscillations, it may do 3 oscillations. We can't say that. It depends on length actually. So the number of oscillations means how many oscillations does the bob do in a given time, in a given second, that we can calculate in terms of frequency. In terms of frequency. Children, it's very important. So here, what is frequency? Frequency will represent with the letter small f. So what is the frequency, dear children, here? Frequency is the number of oscillations completed in 1 second is called actually frequency. Now we will discuss how time period is related to the frequency. Children, here for just imagine a situation where we have taken a simple pendulum with a more length. Let us take. Then here we will get a one doubt. What is the length of the pendulum? How to define? First of all, how to measure the length of the pendulum. It is very important. So if you cannot understand the term called effective length of the pendulum, dear children, so you cannot understand the concept of simple pendulum only. So simple pendulum length, effective length, how can we take? So here what will happen whenever we are doing experiment with simple pendulum, some students, they will take from this point of suspension to end of the bob they will take. That is wrong. That is wrong, dear children. So how to define the effective length, dear children? The distance between from this point of suspension to the center of gravity of the bob. I repeat once again. The distance between point of suspension to the center of the bob is called actually effective length of the simple pendulum. So it's a very important. Effective length. This is a direct question in exam. They may ask you to define effective length of the simple pendulum, or else they will ask us to draw the simple pendulum diagram during its oscillations, and they will ask us to show its effective length in a diagram. So you have to take from this point O, that is the point of suspension, to the center of the bob only. So the distance between point of suspension to the center of the bob is called actually effective length. So now come back to the how time period is related to the frequency. Dear children, if you can take a simple pendulum with a more length, for suppose, let us take this, here is our arrangement set of whatever we made. For example, dear children, if we consider this length is more and it is taken aside, then it is made to oscillate. Then what happens, look at here, means when length is more, it is taking more time to complete one oscillation. Just try to observe here. It is taking a more time to complete one oscillations. Means what? More the length, more the time period. But the thing is that if the length is more, can it make more number of oscillations? No, it is not that. If length is more, because as it is taking more time, means what? It is going happily in a relaxed manner, it is making oscillations. Means more number of oscillations are not possible. For example, if this length is less, for example, its length is less, now it is made to oscillate. Now look at here, it is making a oscillation, it is making a more number of oscillations, and moreover, to complete one oscillation, dear children, in which case is it taking more time to complete one oscillation? So very clear that when the length is more, dear children, it will take more time to complete one oscillation. In a relaxed mode is making oscillations. Whereas when its length is less, dear children, what is happening here? So it is taking, for example, okay, let me show properly. So if its length is less, effective length is less, then what happens? So here to complete one oscillation, it is taking a very less time. Here is very less time. Means here we can make here three conclusions here. Means we can make a relation between length, time period and frequency. Dear children, one very important thing is that here if length is more, more time it will take to complete oscillation. As it is taking more time to complete one oscillation, dear children, it cannot make a more number of oscillation. Which means what? More the time period, less number of oscillations. Less number of oscillation means what? Frequency. So we can say that more the time period, less the frequency. Less the time period, more the frequency. So here we can write here time period, or else frequency is equal to 1 by time period. So it is inversely proportional to the time period. More the time period, less the frequency. Less the frequency, more the time period. Now what are the units for frequency, dear children? Here it is 1 by second, because time period is measured in second. 1 by second can be written as second inverse. It is only hertz it is. Children, whenever you are writing the complete name of the unit, first letter must be small. Of course, here this can be, symbol can be this one. So these are the terms related. So what is a simple pendulum? What are the terms related? Children, what is a simple pendulum here? Let us recall once again. A heavy point mass suspended from a rigid body by means of a string is called simple pendulum. And the distance between point of suspension to the center of the bob is called effective length. And one complete to and fro motion of the bob of a simple pendulum is called oscillation. The time taken to complete one oscillation is called time period. the maximum displacement of the bob of the pendulum from its mean position, either left side or right side, is called amplitude. So, as it is doing oscillations, we can calculate the number of oscillations per second. So, the number of oscillations completed per second is called frequency. Is called actually frequency, and frequency is inversely proportional to the time period. Now, dear children, we will discuss on which factors does the time period of a simple pendulum depends, and even how is it related. It's very, very important. Now, let us see. So, now we will discuss on which factors does the time period depends. Children, so time period of the simple pendulum depends on its length, that is effective length of the simple pendulum. Length in the sense what is, children? Effective length. So experimentally it has been observed that the time period, for example, how can we calculate time period, children? Of course, you will just think that, sir, to complete one oscillation, of course, okay, that is called actual time period. So how much time does it take to complete one oscillation is a time period. But actually experimentally when we are doing, we don't take a time taken to complete one oscillation. Rather, at least we take for 10 oscillations or 20 oscillations. Here we make it a one doubt actually. So why we need to calculate 10 oscillations, time taken for 10 oscillations or 20 oscillations, to get accurate value of the time period. That's it, not more than that actually. So more number of oscillations, you can calculate the time taken for a more number of oscillations, you will get a more accurate time period. Then what we do? First of all, we calculate time taken for 20 oscillations. For example, we will take like this, for a 20 oscillations. To complete 20 oscillations, the time taken is small t. Time taken is small t. Then how can you calculate time period? Time period is equal to t by 20. So when you divide this time with a 20 number, then you will get a time taken for a one oscillation. But with this, what actual benefit do we get? We will get a more accurate value. To get a more accurate value, actually, we will calculate time period for a more number of oscillations and we will take an average. So from that, actually, we can calculate time period. And experimentally, it has been observed that, for example, here, for example, if length is 25 centimeters, if this length, effective length is 25 centimeters, and it is observed that it will take 20 seconds to complete 20 oscillations. Means what? Small t is equal to 20. Small t is equal to 20 seconds. Then children, what is the time period? Time period is equal to small t by 20, because this is number of oscillations 20. The time taken to complete 20 oscillations. But for one oscillations, this is small t by 20. So you will get a 1 second. Example. For example, teacher, if this length is increased from 25 centimeter to 100 centimeters, and it is noticed that the time taken to complete 20 oscillations with this length is 40 seconds. Is actually 40 seconds. 40 seconds. Then what is the time period? See, this is a time taken for 20 oscillations only. This is a time taken for 20 oscillations only. So then capital T is equal to small t by 20, that is 40 by 20. So time period is 2 seconds. Time period 2 seconds. Children, try to understand here. So experimentally it is noticed that if the length of the pendulum is 25 centimeters, the time taken for a 20 oscillations is 20 seconds. Then the time taken for each oscillation, the time period is 1 second. And when the length is increased to 100 centimeters, the time taken to complete 20 oscillations is 40 seconds and the time period is 2 seconds. Now try to observe the relation between length and time period. Look at here, length and time period is very, very important. So dear children, here initially length is 25 centimeters. So time period is 1 second. That is fine. When length is increased 4 times, children, when length is increased 4 times, then time period is becoming double. This is what actually you have to notice. Children, so very, very, very important. Means when length becomes 4 times, time period is increased by 2 times. Means time period is becoming a double. Means how they are related. So it is noticed that time period of a simple pendulum is directly proportional to the square root of the effective length of the simple pendulum. So the first point, Children, understanding this relation is very important. Okay, fine. So the first factor on which time period of a simple pendulum depends is effective length, and experimentally it is noticed that the time period of a simple pendulum is directly proportional to the effective length. So from this only we can make, children, this formula we use to compare the time periods of two simple pendulums with a different lengths. For example, two simple pendulums with a length L1, L2 respectively. Then how to compare their time periods? So for that we use, it is T1 by T2 is equal to square root of L1 by L2. Square root of L1 by L2 means if L1, L2 values are given, obviously we can calculate the time periods. T1, T2 values we can calculate. Okay, fine. Now the second factor on which the time period depends is that acceleration due to gravity. Acceleration due to gravity. Here we may get one doubt. How does it depend on actually acceleration due to gravity? Children, in a motion in 1D, again we will be discussing what actually acceleration due to gravity. What is acceleration due to gravity? The acceleration produced in a freely falling body due to the gravity is called actually acceleration due to gravity. Now we will see how time period is related to the acceleration due to gravity. Children, to understand this, so let us for example consider it's earth surface and here is moon surface. So let us take two identical simple pendulums. Children, let us take two identical simple pendulums. So here is identical simple pendulum in the sense what is, children? Both should have same effective length. So both should have same effective length. So let us say it is a simple pendulum and here is one more simple pendulum. Two simple pendulums which we have taken, and we know that on earth surface G is equal to 9.8 meter per second square, whereas on moon surface it is 1 by 6 times, approximately 1.61 meter per second square. So in which case gravity power is more? Obviously in the case of earth only. So earth has more power to pull the objects towards its center compared with the moon actually. Now dear children, here in the case of earth, dear children, for suppose the simple pendulum is taken aside, here it is taken aside, okay, and in this case also it is made to oscillate at the same time. But dear children, try to understand here, in the case of earth, as more gravitational power is there, the strength of the gravity is more, so as it is taken to the extreme ends, it will try to pull towards the mean position, whereas when it go to this side also, right side, again it is pulled towards this one. So due to which what will happen, as simple pendulum is trying to go right side and it is pulled. When you go to this side, again it is pulled because gravity is more. But whereas in the case of moon, dear children, in the case of moon here, where it is made to oscillation, when it go to the extreme end, just imagine situation, it goes to extreme ends. This gravitational pull is less, right? So what happens, it slowly it will come. Again it will go to this side. Again, as the gravity on the moon surface is less, so again it will come towards the main position very slow. But whereas in the case of earth, when you go to extreme ends, it will come to main position very fast. I will come to main position very fast. Means in the case of earth, when the simple pendulum is made to oscillate on the earth surface, what happens, dear children? It is making oscillations very fast. Means as it is making oscillation very fast means what? It is taking less time to complete one oscillation. Means what? Time period is less. In which case? The case of simple pendulum which is oscillating on the earth surface. Whereas this simple pendulum, dear children, it is making oscillation very slowly because when you go to extreme ends, it is not pulled that much. So again slowly it will come. Means what? It takes more time to complete oscillation on moon surface. So here time period is more here. Children, here more time period, and here is less time period. Now try to think about the relation between time period and acceleration due to gravity. Here less the time period, here more the gravity, less the time period. Less the gravity, that is the less acceleration due to gravity, here is more the time period. So here it is noticed that here both are inversely proportional to each other. Children, it's very important. Means more the gravity, less will be the time period. Why? Because the bob of the pendulum is pulled more, so that it will make oscillations very fast. So experimentally it is noticed that the time period of a simple pendulum is inversely proportional to the square root of the acceleration due to gravity. So here, then how can we compare the time periods of two simple pendulums when identical pendulums are placed at different places? Example, earth surface and a moon surface. So we use this formula, that is T1 by T2 is equal to square root of, it is G2 by G1. Children, here these formulas are very much important. These two formulas we will use to compare when here lengths are given, we can compare the time periods. Here when acceleration due to gravities are given, then we use to compare the time periods. Children, here it is T is proportional to root L, T is inversely proportional to root G. So from this we can write like this, T is proportional to the square root of L by G. T is proportional to root L by G. So whenever there is a proportional symbol, D children, we can take one constant. Let us take a K is a one constant and it is square root of L by G. Children, experimentally a K value is calculated as a 2 pi. So finally T is equal to 2 pi into square root of L by G. So children, this is the expression to calculate the time period of a simple pendulum. Time period of a simple pendulum. And the children, so from this equation only we can calculate the even acceleration due to gravity also. Now we will see the how time period varies with the length. This is T square versus length. It's very important. So the importance of this graph is that, the children, by using this graph actually we can calculate the acceleration due to gravity. But how can we calculate the acceleration due to gravity by using this graph? Children, once again let us recall the expression to calculate the time period. That is, we know that time period is equal to 2 pi into square root of L by G. Children, square on both sides, so you will get it is T square is equal to 4 pi square into L by G. So get this G this side, so it is G is equal to 4 pi square into L by T square. So this also can be written as G is equal to 4 pi square by T square by L. T square by L. Children, here 4 and pi are constant only. If you know the T square L value, T square by L value, obviously we can get the G value. But how can we get the T square by L? That is from this T square versus L graph only. Children, here let us make a graph, yeah, this is, it is x axis and here is y axis. Children, here length is a independent quantity, time is a dependent quantity, and independent quantities always should be taken on x axis, whereas dependent quantities should be taken on y axis. Then we get a graph like this. For a different values of L, if you get a straight line will get like this. So here you may get one doubt. So why don't we get a straight line which is passing through the origin? We don't get a straight line which is passing through origin because the length cannot be 0, right? Length, some value will be there. So here length we can take, what is this sketch pencil not writing? Yeah, here is length is taken on x axis, whereas T square values are taken on y axis, T square values. Children, but how can we calculate the slope here? So look at here. For this, let us take, here is a point A and here is point B. Point A and point B. Now for this, here is one L value and here is one more L value. So this is corresponding one T square value and is corresponding T square value. So look at here. So the slope will be, it is, let us say C. Let us, this point is A. So here children, slope is equal to BC by, it is AC. BC by AC. So children, here BC is nothing but what here? For example, it is T2 square and here is T1 square. Such that it is a L1 and here is a L2. Then BC is given by, it is T2 square minus T1 square by L2 minus L1. Children, T2 square minus T1 square. Again you will get T square value only. So L2 minus L means again you will get length only. So here slope is equal to, slope of the T square L graph is equal to T square by L only. So T square by L is the slope of this graph. So this is nothing but what actually it is the slope. This T square by L. T square by L is nothing but what actually is the slope of this graph. So this also we can write here 4 pi square by slope of T square L graph. T square L graph. So by finding the slope, we will get a value of the slope that you can substitute here. 4 is a constant, you can substitute the pi value, and obviously we can calculate the g value. So this is how actually we can calculate the g value from by using actually simple pendulum. Now we will discuss the factors on which actually time period does not depend. Time period does not depend. So children, it's very important. Before we discuss on which factor does it depend, it depends on effective length and it depends on acceleration due to gravity. So now we will see time period does not depend on the following factor. Does not depend on first factor. It does not depend on shape of the bob. Does not depend on the shape of the bob. Shape of the bob means it may be like this, in this shape, or in this shape, or in this shape. So it is not a matter. It is not a matter. And at the same time, we cannot take like a straight wire. You cannot take a straight wire. So we have to choose a shape in such a way that it make a proper oscillations. And the second one, it does not depend on the mass of the bob. Does not depend on the mass of the bob. Mass of the bob means it may be like a 20 grams, it may be like a 50 grams. But dear children, as it is said that it doesn't depend on mass, I will take a 1000 kg or 100 kg. What happens? This string will get disturbed first of all, no oscillation, nothing. It's not that digital. Of course, it does not depend on mass, but here under certain limits also there actually, means small variation. For example, it is accepted 20 gram force. Example, it's a 20 grams, can be 19 grams, can be 21 grams. So that does not make a difference of time period actually. So that is what actually we have to understand. And here third point, it does not depend on the material. It does not depend on the material with which, means nature of the material with which bob is made. You can use iron, you can use aluminum, you can take a brass also. It does not depend. But actually at the same time here you may get one doubt. Sir, can I take a ball which is made up of thermocol? You cannot take a thermocol. What happens? When you take a thermocol, can you make it do oscillation? Of course, when you leave it, it may come like this, come like this. The moment when you're taking breathing, if you can say, instead of making oscillations like this, it will be doing oscillations like this because your breathing effect. So it is not that. Of course, it does not depend on the nature of the material, but at the same time, it should not be a lightweight material. So children here, of course, these are the factors on which it does not depend, but at the same time, some conditions are there actually. And even the color also. For example, here we have taken a bob which is painted with a blue color. You may even make a painting with a red color, violet. It's not that here. Color also not matter. So children, let us recall. It depends on length. It depends on acceleration due to gravity. It does not depend on shape of the bob, mass of the bob, material of the bob. Okay, children? Fine. Now, one more very important thing is that actually seconds pendulum. Very important. Seconds pendulum. So, what is a seconds pendulum? What is its time period? What is its frequency? And what is its effective length? For suppose, dear children, here is an effective length, let us say. It is an effective length, it is simple pendulum. For example, it is a point B, let us say. Children, to go to point B to C, it has taken 1 second. Again, to come back from C to B, it has taken 1 more second. Which means, now what is the total time taken to complete one oscillation, dear children? The total time taken, 1 plus 1 is actually 2 seconds. Then, if it is possible, if it is okay with this simple pendulum, then this simple pendulum I can call it as a seconds pendulum. Which means what, dear children? The pendulum whose time period is 2 seconds. That pendulum which takes 2 seconds of time to complete one oscillation is called seconds pendulum. Means to go from B to C 1 second, to come back C to B again 1 more second. Such a pendulum we can call it as a seconds pendulum. Children, what is the time period of seconds pendulum? 2 seconds. So here the time period of a seconds pendulum is 2 seconds. Then what is its frequency, children? We know that frequency is equal to 1 by time period. So it is 1 by 2. It is 0.5 hertz. 0.5 hertz. Very, very. Children, this again will be getting in a sound chapter also. So can we hear the sound produced by simple seconds pendulum? We cannot hear the sound produced by seconds pendulum. Why? Because the minimum audible range is at 20 hertz, but it is 0.5 hertz. So we cannot hear the sound produced by seconds pendulum. Of course, regarding this again we will be discussing the sound chapter in detail. And third point, very, very important thing is that what should be the effective length? Children, the effective length of the simple pendulum is 1 meter or it is 100 centimeters. So then only what will happen? The simple pendulum with 100 centimeters length, children, it will take 2 seconds time to complete one oscillations. So children, these are the topics related to the simple pendulum. So once again let us recall what we have discussed. So first we discussed the simple pendulum. What is the simple pendulum, dear children? Here heavy point mass suspended from rigid support by means of a strings is called simple pendulum. And we discussed about the terms related to the simple pendulum. Then we discussed how to calculate the time period and how easy it related to the frequency. Then we discussed on which factors does the time period depends and on which factor does not depend also we discussed. And finally we discussed what is the seconds pendulum and its frequency and the length. Dear children, in the next session we will be solving the numericals based on simple pendulum, and after that we will start motion in 1D chapter. Thank you so much. All the very best.